Hoy, en Toquin TEC, Liliana Arrachea se encuentra con el físico Andrei Bernevig para explicarnos qué son los estados cuánticos topológicos de la materia.
Hi, Andrei. Thanks a lot for coming.
Thank you for the invitation, both to the conference and to the interview and to this wonderful city.
Thanks. So, you are a young physicist. You were born in Romania. You studied in the US. You are one of the top leading scientists in condensed matter physics, but how would you like to introduce yourself?
First of all, I'm not that young anymore. But yes, I was born in Bucharest. I left Romania when I was 18, and I did all my university schooling in the US, and then now work in a field that I find is very exciting, but probably not as well known to the general public as other fields such as cosmology or astrophysics. But it's really a fundamental field of science. It's what you work in, also, and what many people in this world who actually do the science needed for technological advances work in.
Mm-hmm. Yeah, I agree. It's not so well known. And how were you interested in that field?
So when I decided to go to grad school, I was thinking about doing string theory, just as every, or a lot of people think when they leave undergrad and want to go into physics, they want to unify the forces. They want to do Big Bang theory, string theory. So I was on that path too until I realized that you cannot really test anything in string theory. There's no controlled experiments. And if you want to have a field of science which has reality linked to it, or which can test predictions in experiments, then condensed matter is one of the best fields for that. So that's why I decided to go into that field, just to have more connection with the real world.
I see. But did you take that decision in the university already, or before that?
I took that decision before I went to graduate school. I had some conversations with my undergraduate advisor, and they sort of set me straight. They sort of explained to me what condensed matter would be and what string theory would be, and I decided to do condensed matter.
Were you impressed with something in particular, like superconductivity, for instance, or?
I was impressed with the fractional quantum Hall effect. So my undergraduate advisor was Bob Laughlin, who won the Nobel Prize in '97 for the fractional quantum Hall effect, and that's a phenomenon which has deep theoretical implications. Very deep thinking goes into it, but it's also a phenomenon that can be seen in small samples of semiconductors. So that synergy between theory and experiment was something that really attracted me. And my undergraduate advisor was a perfect example of that synergy. So I got lucky. And were you interested in doing experimental physics at some time, or always theoretical physics? I volunteered in a lab a couple of times. It didn't go down that well. I broke some things.
Yeah, this sometimes happened to us.
So then they told me that everything I touch turns to dust. So I decided not to do experimental physics.
Yeah, same thing happened to me once. Yeah. So, and have you ever considered doing something else, but science or like physics?
So I did have a small period between undergraduate and graduate school for about a year where I was a banker.
A banker?
Investment banking.
Wow,
but then I decided that was not for me either. So I went back to school.
Okay.
So I have 1 year of real world experience. So, but I wouldn't trade what I have now for anything.
Interesting. You are working in topological states of the matter. Could you tell us about it?
Yes. So everything we have in our world is, as materials, is classified into metals, insulators, semiconductors, etc. So, for example, a metal is just a material in which electrons can flow and can carry electricity. Now, these electrons, as they sit in the metal and carry electricity, they have a mind of their own in the sense that they collide with each other. And that those types of collisions basically give you heating up of wires as current passes through them, the heating of the laptop that occurs when you put when you watch a Netflix movie or whatever on your lap, and the processor works very hard. Those type of collisions of electrons in metals generate loss of energy and of heat. Mm-hmm. Now, in topological materials, electrons can flow without colliding. So it's kind of like having one-way highways where electrons can just go into in one direction. Now, of course, since we don't really build highways, electrons don't really build highways, don't have a central planning system where you can build where they can build roads. Something has to make them go into just one direction. And what happens in these topological materials is somehow if I have something that's topological that looks like a two-dimensional material, something like this, there's no current flowing through here. Currents only flow through the edge of the material. And because they can flow through at the edge of the material, they can just flow into one particular direction, and that direction is given by information that the middle of the material has or the bulk of the material has. So that's, for example, as you well know, that's the quantum Hall effect. What we're trying to do is to kind of do the next generation of those type of materials. So, for example, if instead of having a highway that just goes into one direction, you have a highway that has both left and right lanes. Normally, if on that highway electrons would flow, electrons that move in this direction would collide with electrons that move in this direction, unless you can sort of separate them, very much exactly like in a highway. Again, in materials, in real materials, that's not very easy to do. And so far, the only way of really doing it is through these topological materials that I'm working on. So, or that many people are working on, rather, I should say. And this is a field that has, I think, both theoretical and practical implications in the discovery of new materials, discovery of materials with exotic properties, and hopefully technological applications at some point.
Yeah. Which is the next step now? What do you think about the next step in the topological race?
I think one of the biggest steps in topological states of matter is what's called braiding. Is basically
so braiding has to do with quantum computing.
Braiding has to do with quantum computing. There's several proposals for quantum computation. So one of them which is called topological quantum computing, has to do with braiding. So braiding is a esoteric fundamental property of particles. So particles in our world are differentiated between bosons and fermions at a very simple level. So bosons, you take one boson here, one boson here, you do a swap, their wave function doesn't change, so their state doesn't change. For fermions, what happens is you take two fermions, you make a swap, and you get a minus sign in the quantum mechanical wave function. Now, this has fundamental properties in terms of materials. There's a reason why all the electrons that we have in our cell phones or in our computers are fermions. It basically tells you, for example, the fact that the wave function of fermions...
Let me just add that fermions are electrons, that electrons are fermions, actually.
Yes. Yes, exactly. Thank you. Yeah. So you cannot put two of them at the same point. And this is the same property as having the wave function, quantum mechanical wave function of the electron changed by a minus sign. You cannot put them at the same point. Now, there's other particles, which are called anyons. So fermions, anyons. Anyons have the property that when you exchange them, they don't get a plus sign or a minus sign. They get some arbitrary phase, say, 1/3. And then there's the other thing, which is called non-abelian braiding, in which very esoteric particles called Majorana, and I'm not sure if he was on a trip to Argentina when he died. Where was he?
Well, one of the theories is that he ended here, actually. It's a story. It's really a funny story of this guy. I saw some time ago in a newspaper from Argentina some review of some article written by a writer who was sure that he has seen in some cafe in Buenos Aires, he has seen Majorana writing equations in some napkin, yes.
In which year was this? In which year was the article?
The article is for less than 10 years ago, so really? Majorana was...
very, very old.
Yeah, it's a very old guy, who knew about the story of Majorana, and he actually worked with Heisenberg some time ago, of course. And after knowing that story and after seeing the picture of Majorana, he thought that this guy
was Majorana.
Was Majorana.
So just to let everyone in on the inside joke, Majorana was this great Italian physicist at Torre Majorana, who was basically, during the time when quantum mechanics was just being developed, and people were trying to find out how many types of particles can exist in nature. So Dirac came up with the Dirac fermion, Wahl came up with the Wahl fermion, and Majorana came up with the Majorana fermion. Now, the Majorana fermion is a fundamental particle because it's in very loose terms. We can call it. We can say that the particle is the same as the antiparticle, which is kind of its half matter, half antimatter. So now the Majorana fermion hadn't been experimentally discovered until, say, 7 years ago, and it's also been discovered in condensed matter, in a condensed matter experiment. Mm-hmm. But Majorana got instantly famous, and then he went a bit nuts, and I guess jumped off a ship. That's the story. Jumped off a ship on the way to somewhere.
Yeah, this is one of the versions.
That's one of the versions. The other version is he was in a cafe in Argentina.
Yes. Well, there is a third version that he went to some monastery.
Ah.
Yeah.
Well, that's
so
the least,
there were,
the least fun version.
Yeah.
I sort of came on that path in 7th grade, and the reason for it is I went to a competitive primary school, and there was this friend of mine who was very, very good at math. Somehow he was always better than me. And then I said, well, I don't want to be number 2 in my primary school. I want to be, number 1 at something. So this guy is better than me in math. He's also my friend, so I can't be jealous. There was very conflicted feelings. And I was like, well, I'm just going to try to be good at something else. So then, physics was the only other hard science that we did. Then I started studying physics, liked it, and then in high school, as I graduated from primary school and went to high school, I had, as it usually happens, I had a teacher who was amazing. She was really inspiring, and that was the end of it. But yeah, it started off as me trying to not be jealous at a friend of mine that was better than me in math.
Andrei, please tell us about the recent technological developments related to that field.
So in the field of topological quantum computing, so when people want to implement qubits by doing this braiding process of Majorana fermions, Microsoft has recently decided to invest $1 billion with a B dollars into the field. they've sort of opened up 3 research stations, one of them which does pure theory in Santa Barbara, California. It's called Station Q, but more recently they've invested a lot of experimental, as you know, experimental money or money for experiments, especially in 2 groups in Europe, in Copenhagen and in Holland.
It's clear that they believe that in the potential of topology.
I think they certainly believe the potential of topology. I'm less certain about the time frame when this potential will be developed, but I'm also very certain that it will be developed at some point. And I think it's important for us as scientists, but of course also for the public and funding agencies and private agencies that fund science to realize that the time frames on which new technologies develop are not immediate. For example, the transistor, when it was developed in the 50s, it was developed by a physicist who won a Nobel Prize for it. Now, nobody knew the effect that it would have on humanity, and really...
It really changed our lives.
Nothing would exist without transistors. Your cell phone wouldn't work, your TV wouldn't work, your computer wouldn't work. Everything that we have, the camera that's filming us wouldn't work. Everything we have in our world is because of transistors, and that was developed by physicists. Now, us as physicists, our job is not to make a technology viable. Us as physicists, our job is to provide a proof of concept. It's the job of the engineers to make a technology viable, and that's exactly what they did with the transistors. The physicists discovered it, they showed that the concept works, and then engineers took over and made it what it is today.
Sure.
Miniaturized.
But in some sense, our area is quite special because we somehow always have the hope that we are going to contribute towards something that could be useful in daily lives.
Yes, in a way we are quite blessed about it because we have, we only need to show the proof of concept. If they don't make it work, it's their fault.
Okay, so coming back to your life, you studied in Romania. You finished high school there, but you went to the US to study in the university. And you went to Stanford. Why Stanford?
So Stanford was a weird story, not a weird story, a funny story, really. As I was applying to American universities, I got into a bunch of them. And then from Stanford, I got a phone call one day. I don't know. I don't know what I was doing. I was probably just a bookworm doing some physics at home. And then I got a phone call from this person in Stanford. His name was Doug Osheroff, and he says, he says, "Hello, I'm Doug Osheroff. Do you know who I am?" And I'm like, "No, I don't know who you are. I'm sorry." He's like, "Well, I just won the Nobel Prize in physics last year." And I was like, okay, that's nice. He says, "Well, would you like to, we accepted you. Would you like to come here?" And the first.
But that was after you applied.
After I applied, after I applied, and I said, he's like, "Do you have any questions?" And my first question is like, "Did I get a scholarship?" And he was like, "Well, I don't know, but I'm going to walk to the center, to the admission center right now and find out and call you right back." And he calls me in like 10 minutes, and he says, "Yes, you got a scholarship." So that's kind of personal involvement of somebody somebody who really. I mean, we know now that our time is very limited, so I can only imagine how limited his time was at the time. It's very limited, and the fact that he took that personal time to call someone like me, who is just a punk and like a 17-year-old punk, that was quite special, and it meant something. So that's why I chose to go to Stanford.
And do you keep in touch with the scientific community in Romania?
Well, not the physics one that much. Most of my high school friends, which are still very good friends with, about 60% of them, are basically work in university, but in chemistry, medicine.
I see.
So I know about the sort of the state of funding in the system. I don't know purely about physics in Romania, with several exceptions. I do keep in touch with some professors in the university, but not with a huge amount.
Okay, I see.
So I think things are getting a lot better, especially because the European Union is pumping money into the newly joined countries. I mean, newly joined meaning 12 years. I think we joined 12 years ago or something. But there's still a massive investment coming from, the west of the Union, Germany. A lot of investment from Germany into science in let's call it developing economies of the East.
Yeah, but it's good to know that. So, to finalize, let me ask you the last question. What would you advise to a person who is starting studying physics right now?
Yes, so that's a very tough.
You have some particular message?
The first message is have fun.
Okay. Yes,
don't do physics if you don't like it. If you wake up in the morning and feel like, I don't want to go and do a calculation, don't do physics. Or it should always be like, you're not going to do physics for money. You're not going to do physics for fame. So just do it because you like it. Now, that's obviously just a life of advice at my very old age. Now, on a purely professional level, I would say, find something that hasn't been looked at, or that's been looked at but you feel people have missed something, and then if you're sure of yourself, just keep. If you're sure you found something interesting, just keep at it. Don't let anybody tell you otherwise. And don't wait for big projects such as solve the mysteries of the universe. Start with something small. There's a treasure to be found in every small thing. And I think that's really kind of like, if you look at all the Nobel Prize winners, they sort of have this type of story. Nobody really wanted to solve the mystery of the universe. They stumbled upon something. They were sure enough of themselves to actually continue looking at that something, even when people around them told them not to. And they obviously had the skills to develop it. But yeah, I would say self-confidence is very important in this field. And yeah, just finding the human knowledge that you get by advancing human knowledge and thinking about things deeply. It's something that you don't find in many other fields, I think. So that type of thing is kind of amazing about theoretical physics, and I would very much encourage many people to go into it, even if they don't want to pursue a career over their whole lives in physics. You can, many of the people on Wall Street are physicists. Many of them ruining economies, so they can do that too.
So thanks a lot, Andrei. I enjoyed this interview. I hope you too.
I certainly did.
Thanks a lot.
Thank you so much. Thank you.